All right, so we have two more examples that I wanted to cover in related rates. There's all kinds of different examples we could talk about. You're going to encounter others in the homework, but the idea here is essentially the same in each case. So what we've seen in the four examples we've done so far is we want to start with some kind of formula, and we've seen that a lot of those formulas are geometric, but they don't have to be. And then we want to differentiate that with respect to time, typically. Then that's going to create a bunch of rates of change, and we're going to search through our problem and see what quantities are we told are given in that problem. Which rates of change do we know? Which quantities are we given for the variables? And if we're missing any information, can we find it? And we plug it in and try to solve for whatever the problem is asking us for. I think the hardest part of these problems, especially once we get up to these kinds that we're about to encounter, are it's the setup. You know, people struggle with setting the problem up. It's not the calculus that's the hard part. It's knowing how to model what's being described to you mathematically. So let's take a look at this one. It says a kite 100 feet above the ground moves horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string has been left out? So you definitely want to draw a picture for this. And again, you get to laugh at my art skills here. So here's our little friend standing on the ground, holding the string to a kite. So the kite's kind of, blowing in the wind. Here's our kite right here, little tail or whatever. And we're told the kite is 100 feet above the ground. So I'm going to label that. One thing I want to point out, I should have mentioned this in the last video actually, when we did the diagram of the boat. I'm going to go back to that for a second. You'll notice in my diagram, some of the quantities that I label are constants and others are not. Others are just given letter names. Even though in the problem we're told certain quantities to assign to those letters, those that R and that D maybe, why am I not using those values in my diagram? Well, there's a convention here that's really, really important to pay attention to, and that's this. You don't want to label any quantities in your diagram using a number unless that quantity is actually constant. So what I mean by that is the height of this pulley does not change in this problem. It's always 1 meter. D, for example, even though I'm told, when the boat is 8 meters from the dock, so that would be like assigning 8 to D here, that quantity is changing over time. This only happens at one particular instant in time, but over the course of time, this value D is decreasing. So that makes it variable. It's a variable, not a constant. And you don't want to, in your diagram, put constants in there unless it's actually constant. The reason for that is because when you then try to create an equation like we did over here, if I had written D as a constant instead of just D, then that would have gone to 0 once I differentiated, and the entire right-hand side of my equation would have been 0. I would have been getting something that I have no hope of solving. So you have to be very, very careful of which things you label as constants and which things get letter names for variables. That's enough on that. So over here, we're told that the kite is 100 feet above the ground, and we're given no indication that that height is changing. So we're going to assume that the height is constant. That's why I'm writing it as 100. It is moving, though. It's traveling, at a constant rate of 8 feet per second. I don't need to include the 8 feet per second in there. I'm not going to do that. It says, at what rate is the angle between the string and the horizontal decreasing when 200 feet of string has been left out? Now, technically, you can kind of nitpick here and say that my little person is holding the string above the ground, right? But we're not told how high. That ultimately doesn't matter. So the angle that we're talking about, if I were to call that angle theta, I can think of this as the horizontal, but notice that it's parallel to the ground. If I were to extend that line representing the string to the ground here, that angle and that angle are going to be exactly the same. So I don't need to concern myself with how high the string is above the ground. It's just the angle that I'm interested in. And notice that creates this right triangle for me, which is kind of convenient. So again, what information are we interested in here? The kite is 100 feet above the ground. We've labeled that already. We're told at one point that the string, we're looking for the moment when the string has 200 feet in length. So when this 200 feet of string has been let out. I'm going to interpret that as the hypotenuse of this right triangle. And even though I'm tempted to write 200 there, I don't want to do that because the length of that string will change as the kite flies further and further. I'm going to call that S for string. Okay, and then the base of this little right triangle is, we're going to think of that as, I'm going to call it H for horizontal. It uses the word horizontal in the problem. That seems appropriate. So once again, we have this right triangle. All of these quantities are related in some way. And I want to look at what it is I'm trying to get out of this problem and what information I have. So it says we're moving at horizontally at a speed of 8 feet per second. That's going to indicate the rate of change in h, right? H represents the horizontal distance that this kite has traveled from directly above our little kite holder right here. Again, ignore the little discrepancy with this string right here. It's not relevant. So that tells me that this 8 feet per second is dh dt. That's what that represents. So my original equation that I come up with had better involve that h somehow, because I need to be able to differentiate it to make a dh dt show up so that I can use that. What else do we need to know? Well, it says that what else do we have? 200 feet of string has been let out. So we know that the instant in time that we're interested in is when s is equal to 200. So here's what I'm thinking. We are also given this theta here, and what we're trying to find is the rate at which that angle is decreasing. Now, hopefully you can see why that angle should be decreasing as this kite moves horizontally towards the right here. This string is going to kind of go down. You know, it's gonna you know, this will move out. The string will kind of move down in its angle here. But that's d theta dt that we would be looking for there, the rate of change in that angle. So I need to get theta involved in here somewhere as well. And this is where I'm going to use trigonometry. What I'm going to do is set up a trigonometric ratio to relate theta to two of the sides of this right triangle. And I'd like to use the 100. I'm going to do this. Tangent of theta would be equal to opposite over adjacent, 100 over h. Okay. Next thing I want to do is, as we've seen, differentiate both sides of this with respect to t. So tangent of theta, its derivative is secant squared of theta. Secant squared of theta, but then I have this d theta dt that's going to pop out there. And that's the thing that we're ultimately trying to solve for. Over here I have 100 over h. Its derivative is negative 100 over h squared, but then I also need a dh dt to show up there. All right, cool. So let's see. Do we have all the information that we need? I have dh dt, that's 8. I don't have h. I have s, but I can use that to find h. We're going to see that in a second. Do I know theta? Well, it doesn't tell me theta either, but believe it or not, I can actually find both h and theta using the information that we have. So let's do that first. If s is equal to 200, that's what we're being told here. I'm going to replicate this right triangle, but here I'm going to actually use the constant 200 there. According to the Pythagorean theorem, this side is going to equal 200, the square root of 200 squared minus 100 squared. You can work that out. That's equal to 100 root 3. It's a straightforward Pythagorean theorem type of problem. Okay, so h is equal to 100 root 3 at the instant in time that we're interested in. Okay, is there a way to determine theta there? Well, yeah, actually, I can find theta pretty easily using an inverse trig function, but I actually don't even need to, because if you notice where theta appears in this equation, I'm doing secant squared of that. So I can find secant of theta without ever knowing what theta is, as long as I know all of the sides of this right triangle. In fact, I really only need 2 of them. So secant of theta is the reciprocal of cosine, adjacent over hypotenuse. So the reciprocal is hypotenuse over adjacent. That would be 200 over 100 root 3, or simplify that to just get 2 over root 3. Okay? That means secant squared is this thing squared. So let's go back up here now. Secant squared is 2 over root 3 squared. Still d theta dt is the thing we're solving for. I don't know what that is yet. Negative 100 over h squared. So now I need h, but we found that, right? It's 100 root 3. So that's equal to negative 100 over 100 root 3 squared times dh dt, which we know is equal to 8. And I know it's tempting to bust out the calculator here. You can do this faster in your head if you know what you're doing. So squaring this is just 4/3 d theta dt. Don't get too wrapped up in the squaring and the arithmetic here. 100 squared is whatever it is, but I have 100 over that. So this 100 will cancel with one of those 100s, leaving me with a 1 on top and one of the hundreds down here. Root 3 squared is just 3. So 3 times that 100 is 300. This is equal to a 300 in the denominator. And then down here, I have a negative 1 on top that's left over after canceling, times 8. That's equal to negative 8. Okay? I can solve this by cross-canceling now. Or, multiplying by the reciprocal of that. So d theta dt is equal to negative 8 over 300 times 3/4. Do yourself a little cross-canceling here. That's going to give me a 1 and a negative 2. So I have negative 2 over 100, or negative 1/50. Now finally, what would the units of measure be here? Well, theta is an angle, and we said previously in calculus we only ever deal with radian measure when we're talking about angles. So this would be radians per, what is our unit of time? Up here I see seconds, so per second. Okay, as you can see, that problem was more involved than the ones we've done before. And where it starts to become more involved, after you've figured out how to set the problem up and you've taken your derivative, the derivative, honestly, is probably the easiest part of the whole problem. That's what's kind of ironic about these problems. You first learn them in calculus, but the calculus is the easiest part. The difficult part, I think, for a lot of people is seeing all of these different unknowns here and trying to figure out where to get the information to plug things into those comes from. Some of that information comes from the problem, but in our case, we had to find some of that other information. So it gets a little bit involved. Here's our last example, and this one's also going to involve some trigonometry. It says a lighthouse is located on a small island 3 kilometers away from the nearest point P on a straight coastline, and its light makes 4 revolutions per minute. How fast is the beam of light moving along the shoreline when it's 1 kilometer from P? So I'm going to, again, draw a diagram for this. This little dot here, I'm going to imagine that's my lighthouse, and here is my straight shoreline. So we know that the shortest distance between 2 points is a straight line, and because the shoreline is also straight, that's going to be a line that's perpendicular to that shoreline. We're told that that distance is 3 kilometers. 3 kilometers away. And we're calling that point P right there. Okay, now what's going to happen is this light, from this lighthouse, it's rotating. That's how a lighthouse works. And at some point in time, we're going to have a beam of light shining down here. This distance from P to this point here is going to be changing because as the lighthouse rotates, that beam of light is moving, constantly moving in this repetitive pattern. And so I'm going to assign a name to that. I'm just going to call it S. S for shoreline, I guess. So it looks like we're building another right triangle that we're going to have to use somehow. Now, another thing that's going to be relevant is the angle up here, theta. Okay, So as this lighthouse rotates, we're told that it makes 4 full revolutions per minute. What is 1 full revolution in terms of radians, in terms of angle measure? 1 full revolution around a circle, we think of that as 2 pi radians. So 4 revolutions would be 4 times that. 4 times 2 pi would be 8 pi. So that means that our the angle is changing at a rate of 8 pi radians per minute. And that angle is exactly this angle right here. So notice the change in theta from this perpendicular line to this hypotenuse of this right triangle as time passes is the same as the change in our angle in the rotation of this lighthouse. So I can write off to the side d theta dt is equal to 8 pi radians per minute. Right, that right there, before we've come up with any equation, is going to be something that stumps a lot of students if they try this on their own. Just getting that quantity from the information that we're told in the problem. But now that I have that, I can kind of start plugging away at the rest of this. So looking at this one more time, what information are we given? What things are worth labeling here? I think actually we have everything labeled that we want to have labeled. S is changing, the 3 kilometers is not changing, theta will be changing. So how can I relate the quantities in this diagram? Well, I have an angle and I have an opposite and adjacent side. So I'm going to use tangent again, since that relates to the opposite and adjacent sides. Tangent of theta is equal to opposite over adjacent, which would be S over 3. And once again, I know I'm going to have to differentiate this with respect to t. So I'm going to go like this. Differentiate with respect to t. That gives me secant squared again, secant squared of theta, d theta dt equals, the derivative of this would just be 1/3 ds dt. Okay? And notice ds dt would be the thing we're looking for. It says how fast is the beam of light moving along the shoreline when it's 1 kilometer from P? Well, that's the same thing as saying at what rate is this leg of this right triangle S increasing? At what rate is that increasing? Because that's telling me the same exact information. So I'm looking for ds dt. What information do we have? We have d theta dt. We found it here, so I can plug something in there. I don't know what theta is, but in the previous problem, we saw that we don't actually ever have to solve for theta as long as we can find secant of theta. And to do that, we just need the relevant sides of our triangle. So I'm going to redraw this triangle one more time, like we did in the last problem. 3 kilometers here, and this time we're looking at the specific instant in time when the light is 1 kilometer from P. That's this leg of the right triangle right here. Okay, so using the Pythagorean theorem, that would mean my hypotenuse is root 10. That's straightforward to deal with. So now with this, I know that secant of theta, and remember theta is up here, would be hypotenuse over adjacent. That's root 10 over 3. So now we can plug that in for the secant of theta up here. Secant squared of theta would be this thing squared. Root 10 over 3 squared. D theta dt we found over here, that was equal to 8 pi. That's equal to 1/3 ds dt. I can solve for ds dt by multiplying both sides by 3. So that gives me this. ds dt equals 3 times this thing squared, which would be 10 over 9 times 8 pi. Do a little canceling there. I'm going to get 80 pi over 3. And then once again, make sure you're using the right units. So this is a measure of length and or distance. We've been measuring distances in kilometers. And the units of time that have been appearing here have been minutes. I see minute there. So that's kilometers per minute. And there it is. That's going to wrap up section 3.9.